Hey guys, it's your boy Chili here. Welcome back to Hardware 3D. Today I've got a little bit of a treat for you. We're going to be making a dynamic vertex format that can be defined and queried at runtime. And we're going to be doing this using a little bit of template metaprogramming techniques. And that's something I haven't really covered in much depth in the C++ series. So it'll be fun to play around with that stuff a little bit here. Now, one thing I want you to know is that, I haven't covered this stuff in much depth, and I can't, do an exhaustive explanation of template metaprogramming in a single video. But don't worry, it's not required that you understand the mechanics and the internals of this system that we're going to create here today. As long as you understand the interface, you're going to be fine for the following tutorials. So if your eyes start to glaze over during this video, don't worry about it too much. As long as you understand the interface of the thing that we're going to create, that is all you really need. Now, before we talk about the implementation of this system that we're going to create, I think it's very important to talk about the motivation. Why are we doing this? Knowing the motivation really helps you to understand why the system is made the way it is. So, what is our motivation? Well, let's look at what we've been doing up until now. Let's say we want to create a skinned box. So, we create a vertex format as a structure here. This is static, known at compile time by the compiler. And it has, channels for things like texture coordinates. And then in cube.h, we have function makeSkinned, which accesses that member. So if we were to pass in a vertex format that didn't have a texture coordinate, we'd get a compile time error when the compiler couldn't access this member. It all works fine. Now, what are we going to do in the near future? Well, what's the name of this tutorial arc? We call it the ass leg, right? The ass leg, because we're using assimp to load models at runtime. Well, if we're loading a model at runtime, it's all dynamic, right? And we could have situations where we want to make it fully dynamic. We don't know what kinds of channels this model will require. Will it require a normal channel? Will it require a texture channel or multiple texture channels? We don't know. So that means that this system of checking this stuff at compile time isn't going to work. Let me tell you what I would like to do. It's not possible, but we'll get into that in a second. What I would like to do is if I pass this structure to some function that loads a model, it could inspect the structure of the structure, and it could see, oh, it has a texture coordinate channel. Let's make sure that this model also has texture information, because if it doesn't, then we have a mismatch, and we could throw an exception. The problem is that C++ currently does not have that ability. That ability is called reflection, the ability to look at your data types at compile time or at runtime, and to see what are the members, what are their names, what are their types, to enumerate them, and then to do some processing based on that information. C++ doesn't have reflection yet. It might get it in the future. But for right now, we're basically up shit creek without the paddle. So what that means is that if we want to do that kind of checking at runtime, we'd actually have to create another structure or some kind of data at runtime that exists in memory that describes this structure. So we'd have to describe the structure, and then we'd have to describe the structure again. Does that sound familiar? Yeah, because that's exactly what we're doing down here. Except now right now we're duplicating that information twice. It's actually 3 times because it's also duplicated in the shader. But now we'd have to duplicate it 4 times, which is even freaking worse. I would just like this to be automatic. And that is where the dynamic vertex format system comes into play. We're going to develop a class, or actually a system of classes, that allows us to define our data format like we're doing here with a structure, but it also allows us to access that data with hopefully some very nice syntax. And it's going to be huge. It's going to, in the end game for this, it's going to allow us to have a single point of definition that all the other code will just react to and will automatically adjust to. So that means we can get rid of this. We can get rid of this struct here. And what it'll actually mean, the end game, is that there'll be one definition for the input of a shader, and that will be in the HLSL code. And all the other code will react to that dynamically at runtime. We won't get there in this video, but sometime in the future. It requires something called shader reflection, but we can get pretty close already in this video. All right, now let's take a look at the actual system that we're creating here. It's in a file called Vertex Layout.h, and this contains 3 classes. First class is the Vertex Layout, describes the layout of the vertex, what data members it has, and basically their relative order to each other. What else do we got here? We have a vertex, and this is an interesting type, and I'll get into the system in a sec, but it's kind of like a proxy that allows us to access the data of a single vertex. Because basically, now that we're managing all this data ourselves, the data is just going to be stored in a big array of bytes. And we are going to impose the structure and the interpretation of those bytes ourselves manually instead of the compiler doing it for us automatically. Which is something that you don't often want to do unless you have a good reason like we have right now, which is we need that dynamicism, we need that reflection. So we have to implement it ourselves. And then we have the Vertex Buffer, which is the actual buffer of bytes. So Vertex Layout basically consists of a number of elements. And this is just vertex elements that you would normally see, position, a 2D position, a 3D position, texture, normal, color, that sort of stuff. Those are the kinds of elements that we find in our vertices. So I have an enumeration for element type, and then I have a class for element, and the layout just has, let's see if I can find it, just a vector of elements. We can see here every element it's very simple. It's just the type of the element and its offset in the vertex, number of bytes from the beginning of the vertex. So the first element is going to have an offset of 0, and the rest of them are going to depend on the sizes of the elements before them. And then in the element here, we just have a bunch of utility functions. It's not that complicated. Get the offset into the vertex after the current element, which is just this element's offset plus the size of this element in bytes. We can get the offset of the element. We can get the size of the element, which is the size of the type. And then we have a function here to get the size of the type, which is a constant expression function, so it doesn't take up any runtime computation. Just a big switch here that translates our element types into the actual underlying system types that will be used. So that stuff's not that complicated. Now we get into the actual, the Vertex Layout itself. So there's some complicated stuff here. Now we're getting into the template stuff. So the most important thing here is the ability to resolve an element given an element type. So let's say I want to access the 2D position element in this vertex layout. I want to know, usually when I'm doing that, I want to know its offset in the actual vertex data so I can, modify it. So what I would do then is I've got this template here, and I would call resolve with the element type that I want, like position 3D or something. And all it does is it loops through the elements. It finds the one that matches this type, and then it returns that element as a constant reference. And so that's very simple. The other way to resolve is to resolve by index. If I know the index of the element in the container, I can just, do that automatically without having to loop. Very simple. And again, if you want to build a layout, you're going to have to append elements to the layout. So we have a function for that. And we have a function to get the size of the entire vertex, which is to say, if we get the offset after the last element, that will be the size in bytes of the vertex. So far, Vertex Layout, hopefully this isn't too mystifying to you. Seems fairly simple. Now here is where things get tricky. This vertex type here, you might expect it to have, a buffer of bytes or something that represents the vertex, but it actually has no concrete data of its own. It exists as a proxy or as a view into a vertex that exists in the vertex buffer. So you can see it's private data. It only has a pointer and then a reference to a vertex layout. And you might be saying, that seems a little weird. How does that work? Well, let's skip this for now. Let's first look at a vertex buffer. what is that? So if we look at the private data, we can see that a buffer basically consists of just a vector of bytes. Those are the bytes of all the vertices, and then a layout that describes, the structure of those vertices. So an unstructured byte buffer, and then a description of the structure that we are going to impose on top of that. So Vertex Buffer is constructed with a layout. We can get the layout, obviously. We can get the size of the Vertex Buffer. And I should make it clear here that this size isn't in bytes. This size is actually in vertices. Now, the InPlaceBack function allows us to construct a new vertex in place at the end of the buffer. And this is where we get into the template metaprogramming. So I'm going to skip this one for right now. We'll get back to it in a second. But let's look at some other stuff. We got back and front, which returns a vertex, which, as I said before, is a proxy view into some data in the byte buffer. So we can get the first and the last vertices, which is sometimes useful, and we can access a vertex by its index. And we just use some pointer arithmetic to get at that vertex. We create a view into that vertex and we return that view. So far, besides this InPlaceBack, which we have skipped over, I think it shouldn't be too complicated right now, although we still don't understand the nature of this vertex proxy type or view type. So that is what we're going to look at next. This is probably the most complicated part of the design. All right, it's diagram time. So here's the idea of the vertex buffer. It consists of just a flat, dumb buffer of bytes plus an object, a layout object that describes the elements in this buffer, their higher level structure. And then we have this vertex view type, which consists of a pointer to the vertex data and a reference to a layout on how to interpret that data. So let's say that the client, user of the vertex buffer, wants to access vertex number 2. This is going to return a vertex object. So how does that object get created and returned? Well, the vertex buffer, it looks at its layout and it can get the size of a single vertex in bytes. So if I ask for vertex number 2 and the size is, let's say 8 bytes. What it'll do is it'll go from the start and it'll go, this is element 0, this is element 1, this is element 2. And so it's going to create a vertex that has a pointer to this byte here, and it's going to have a reference to this layout. Now that we have this vertex, we can use this vertex to access, the individual elements in here. The way it works, there's a single template function here called attribute, attr, and the template parameter is the element type that you want to access. So you would go, attr of position 3D, and what it's going to do is it's going to resolve an element object from that element type, and that element object is going to contain the offset of that element in the vertex. Then to get the address of the actual element in there, you would take the p data, which is the pointer to the beginning of the vertex, plus the offset of that element in the vertex. That gets you to your pointer attribute. And then you're going to do some compile time constant expression, basically kind of like a switch here. And you are going to reinterpret to the actual type that corresponds to that element type. So if it's a position 3D, you're going to cast to float or XM float 3, and you're going to return that. And this is auto, so it'll automatically it'll template to the proper return type. And then you can just access it like this, vbuff at 2 dot attribute position 3D is equal to blah, which is analogous to the situation that we had before when we were using structures. We could just do vbuff.2 dot position is equal to blah. So it allows us to have a similar syntax to what we were having before, to semantically in our code access particular members by name, but now it's all stored dynamically in this buffer, and all the information about the layout is all stored and built at runtime, so it can be queried at runtime. And that is basically what is at the essence of this whole system, especially the template metaprogramming bullshit part of the system. But there are a few other functions in here so far. Besides accessing an attribute by its type, the element type, we can also access it by index. So in that case, we get an index and we get a value that we want to set to that. And it has a similar start to attr, except now we are resolving the layout element by index. And then we switch on the type of the element, and we call a little helper function here, set attribute, which is templated on the underlying data type. And we give it the pointer to the data, and we give it the parameter. Now, this thing is a template. This is a template programming meme. These double reference ampersands here, this doesn't actually mean our value reference. It means a universal reference. So what this enables is something called perfect forwarding. And I'm not going to get into it because it's just too annoying to go over in this video. But what it allows you to do is to forward a parameter without losing any information, without losing any modifiers on that parameter. So you take a parameter in by double ampersand reference, and then you call std forward on that parameter, and you will not lose any modifiers on that parameter. You'll just forward it as is to the next thing down the line. If that makes any sense. If it doesn't make any sense, if you're interested, I encourage you to, do a little Googling. The keywords are universal references and perfect forwarding, and that'll take you down, a rabbit hole that might be a little weird, but it's useful stuff when you're doing template metaprogramming. Anyways, so set attribute. So here we just do a little bit of safety checking to make our compiler errors easier to debug, and we make sure that the types of source and destination are assignable. Source is going to be, the parameter that was passed in to set attribute by index, this value here, and the destination is going to be this one here. So if someone passes in, something, we want to make sure that that something is assignable to type xmfloat2 before we do this type coercion, which is going to, cause problems if they aren't compatible types. I might even be able to make this a static assert. I don't know. But anyways, it doesn't matter that much. So yeah, that's set attribute. And then here we have set attribute by index. And this is where things get tricky. This is the beginning of tricky stuff in template metaprogramming. Because what this is, and again, I can't go into it in super detail, but this enables us to do this thing here where we can emplace a type. Because what emplace does is it takes the constructor parameters and it constructs a new object from those parameters. But the number of parameters and their types aren't fixed. So that's a problem. If we don't know ahead of time how many parameters we're going to get and what they are, how do we construct a new object? And the way we do it is by template recursion. So here's your quick maths crash course in template recursion. So let's say you've got a parameter and using, universal references, perfect forwarding, and it looks something like this. It's got these dots in here, and then we'll call this one, args. What this is, we call this a parameter pack, and it can be one thing or it can be multiple things. You can have 3 arguments, 4 arguments, and they're all packed into this single variadic template parameter here. So how do we get this? Well, you might think, we'll just loop over each of the elements of this pack and then process them one at a time. But you can't loop over these things. It's not possible. and that's where the tricky comes in. You have to do it using recursion. So what you do is you split this into a function that takes a type of, let's say a type first and a type rest. Notice universal references, and notice first is just a singular argument. Rest is a parameter pack. This is how you do it. So what this does is this takes this parameter pack, which can be 1 or more arguments. We'll say 2 or more. And it peels it off into one singular one, and then 1 or more here. So this is 2 or more. This is 1 and 1 or more. And then what you do with the rest is you feed it back into here. And you keep doing that. And every time you process this, you peel one off and process it, peel one off and process it until you've peeled all of the parameters out of this pack and you're done. Now there's some tricky things here. For example, I said this is 2 or more. What if this parameter pack contained 1? Well, that 1 would go here, nothing can go here, and you'd get a compiler error. So you have to make sure that when you call this with a pack, there has to be 2 or more. So let's take a look at how that looks in the code. Like I said, I told you this was a very quick maths explanation. So if you've never seen this before, you're probably going to be scratching your head. If you've seen it a little bit before and you have a vague idea, maybe this will remind you, but that's about all it's going to do. If you really want to learn this stuff, again, you can look up parameter pack and template recursion, and that'll set you on the right path. But let's see how this works. So we've got set attribute by index, which takes the index. That's easy enough. And then it takes one peeling parameter from the pack, and then it takes the rest parameters. And what it does with the peeling parameter is it calls set attributes by index with the single parameter. And that just sets that attribute. That just sets the data into there. And then we do the recursion case where we take the rest of the parameters and we call set attributes by index, which let's say there are 3. Let's say someone called set attribute by index with an index and 4 parameters. That'll resolve to this function here. One of the parameters will be peeled off. 3 will remain. That will recurse and resolve back to this function. And then we have 1 and 2. That'll resolve back to this function. And then we have 1 and 1. So in the case where we have 1 and 1, again, the first one we'll call here, it'll set this thing. Then we'll call set attributes by index with rest, but rest is only 1 parameter. That will not resolve to this one, because this one requires 2 or more. So the second call here will also resolve to this one. And that's the terminal case. So when you call set attributes by index with a single index and 2 parameters, that is going to, this one will resolve to here, and this one will also resolve to here, and the recursion will be terminated, and you'll be done. And that is how it works. But anyways, so that is how in-place back works. You get a bunch of parameters that are the parameters that are needed to initialize a vertex. The first thing you do is you resize the byte buffer to accommodate another vertex. So now the bytes at the end of this buffer here, they are going to correspond to the last vertex, the one that we are emplacing. So we set all the attributes by index. So we start at index 0, which is the index of the first attribute, and we pass it all the parameters. That is going to resolve to this boy up in here. We set the first parameter, or we set the first attribute, and then we set all the rest attributes recursively. Now, I believe there's a bug in here. Well, it'll be fixed in a later commit, but this should actually be I plus 1, because as we recurse, we have to increase the index. And there you go. Now, this is not strictly necessary. You could certainly do without an in-place back function, but I think you'll agree it's nice to have. And that's sort of the relationship of template metaprogramming. A lot of it is just stuff that isn't strictly necessary, but it's nice to have. And what you're trading is you're trading some nastiness, some fairly complex programming constructs on the back end for a little bit of a nicer interface on the front end. And whether that trade is something that you're willing to make depends on many factors. But anyways, regardless, that is the system. That is how it works. Again, as a little refresher, Vertex Layout describes the structure of a single vertex. Vertex is actually a view into the Vertex Buffer data of a single vertex. And it gives us some very nice members that allow us to access individual attributes by their name. And then the Vertex Buffer just is the actual data of vertices. manages the raw buffer and associates a layout with that raw buffer. Now, if we look at the commit history, we see that besides adding Vertex Layout, we also modified app.cpp, and all I did, I just wrote a little dumb function to test out to make sure I could compile without errors and to make sure that things seem to be working the way they are working, or the way I want them to. And here's the basic usage of the system so far. We create a Vertex Layout, we append a couple of elements, position 3D and a normal. So we have described the vertex here. And then we create a vertex buffer based on that vertex layout. And then we add a vertex using in place back. We add one vertex to the buffer, and then we access a vertex by index using the attribute by name here. And I just stepped through this with the debugger, and it worked. Sort of. We'll get into that in a second. But anyways, it compiled, and I was fairly happy that my template metaprogramming bullshit actually worked, because it's not something I do very often. But let's move on, because we've got some more commits. But hopefully the description of these ones will go fairly smoothly now that I've described the basic concept. Vertex Layout template system working. So before it was Justice. I don't know why I named it Justice. It doesn't really make much sense, but I did it. I might have been drunk, to be fair. So we've added a member here, get element count, which is just an interface function to get the number of elements in the layout, which apparently I guess was necessary. But anyways, it seems like something that you would want anyways. And here I fixed that bug that I was talking to you about before, where when we do the template recursion, we have to be incrementing the index every time so that we're setting subsequent attributes. We're not setting the first attribute every single time. We are, moving through all the attributes. We're basically iterating through them, but we're doing it recursively. And here I do a little bit of a sanity check to make sure that when someone does in place back with a bunch of parameters, the number of parameters that was passed in the parameter pack should match the number of elements in the layout. And if it doesn't match, I mean, you're either missing parameters or you've got too many parameters. Either way, that's probably something that the programmer should be made aware of. So we do a little assert here. Note that we can't use a static assert because the layout is dynamic, so we don't have that information at compile time. There you go. This is working. App.cpp. I do a little bit more of a full-on yummy test, putting a bunch of vertices in the buffer, but you get the idea. All right, now we get into some more juicy commits. We're adding new features and refinements to our system here. So const vertex handle, vertex.h. So I renamed Vertex Layout to just Vertex, because it's not just a layout in here, it's a whole Vertex system. But anyways, so the constructor is now protected this is Vertex, and I create a new type, which is const vertex, which is the same as vertex, which is to say it's a view, but this view cannot be used to manipulate the data, only to read. So when I call atcher, this is actually now it returns a const reference. But you can see it's very lean because it basically reuses all the code from the non-const version. It just wraps it a little bit so it's made to be constant. It's the same concept as with iterators. You have const iterators and non-const iterators. We also have const vertex and non-const vertex. So now in back and front and the operator here, I've added new versions, overloads for constness. So if the vertex buffer is const, then when you call back on it, you will get a const vertex instead of a normal vertex. Just adding support for const correctness to our vertex system. And that was tested out here, and it worked to my satisfaction. All right, now for a true test of our layout system, actually using it to render something. So we are going to rewrite the Suzanne AS test to use our dynamic vertex system. So there's a lot of stuff in here. Let's look at the AS test. First of all, let's look at app.cpp. We delete the F because obviously it's not needed anymore. Now in the AS test, we include vertex. We lose this structure here because now we're going to be defining our vertex dynamically. So we create a vertex layout. You see I've put it inside of a namespace because of collision with other stuff. Then in as test in here, we don't need this structure anymore because we're defining everything dynamically. So you can see right away, I put stuff here inside of a namespace because I had some collisions. So I use an using on Vertex Layout so I don't have to prefix it. And then I create a Vertex Buffer. And in line with that, I create a Vertex Layout and I append position and normal to it because that's what we were using. Use std move with that to pass that into the Vertex Buffer. And then this is all the same. We don't create vertex for vertices or reserve or anything in here. All we're now doing is we're looping through the vertices and we're using in place back on our Vertex Buffer. This is our template metaprogramming bullshit function at work here. And yeah, basically the same as we were doing before. Pass in XM float 3 that's been scaled and reinterpret cast another XM float 3. It's working basically the same. And then down here, add static bind. Instead of passing in our vector, we pass in our Vertex Buffer. So this means for the constructor for Vertex Buffer, it's probably going to need some changes. And if we look at vertexbuffer.h, we see indeed it has added a new constructor here that takes in hardware 3D exp Vertex Buffer. Why did I name it this? Who the hell knows? I was probably drunk. I think I mentioned that already. Not a joke, actually coding drunk. But anyways, and yeah, it's the same idea, except now that we have a Vertex Buffer, we can use, vbuff.getData to get access to the bytes, vbuff.size to get the size, and the stride is gotten by vbuff.getLayout.size. That's the size of a single vertex in the buffer. And finally, vertex.h, some things were changed. I mean, obviously, like I said, namespace was added. I'm pretty sure the getData function is new, though. And that's really the only major change. And I mean, if you run it, I believe there was a bug, because the next commit says fix problem with Vertex Buffer initialization. vcount to buff bytes. So what the hell does that mean? Probably some kind of mix-up here. So here, byte width, I was setting that as the size of the Vertex Buffer, but the size of the Vertex Buffer is actually the number of vertices, not the size in bytes. So I imagine I added a new function here, size bytes, which gives you the size of the buffer in bytes. And then it worked, and it wasn't weird. So yeah, that's our system working. I'm not going to build it and show it on the video because it looks exactly like it did in the previous video. There's no changes here to the features. It's all stuff under the hood. Things are being managed completely differently, but the view of the application remains the same. Now here, I just do a little refactoring of our template code. So let me show you here. There's a little bit of technique here. What do I do? So I add template element type structure map. So this is structure that's templated on element type. And this is a little bit of template metaprogramming technique. And it basically allows you to map type names to some kind of structure that contains compile time data. So it basically works as a compile time lookup table. And the way how it does that is it works with template specialization. So when I specialize, so I define this templated type, that's template on element type. And then I define specializations, and each one of these specializations gives me some different data. So when the specialization is position 2D, then the system type is going to be XMFloat2, and the DXGI format is going to be RG32 float, and the semantic name for the shader is going to be position. And we have all these different template specializations, and that allows our code to be a little cleaner, and it allows us to define these relationships between element type and system type and stuff in a single place instead of having them all scattered throughout the code. Because when you want to make a change to one of these definitions, if it's scattered throughout the code, you're probably going to miss one and you're going to introduce a bug into your system, which you may or may not realize until much later on, if ever. So we do that. And now when we want to get, for example, if we're doing a switch and for position 2D. Now we can look into the map on position 2D and get the sys type like that. And that's much slicker. And here, this append function here, this isn't really, there's no reason to make it templated. There's no reason to make it compile time. You might as well just take it in as a runtime type. And then, because you're just emplacing it back as a runtime type anyways. So I just removed the template from here because it didn't make any sense. It was superfluous. Now here is a situation where our template structure map is going to look very nice. Because before, we had this big if const expert chain of branches, compile time branches, but still branches. And we can replace all this bullshit with this. One resolve, one call to resolve, and then all this stuff gets replaced by a single lookup into our map based on the type that was passed in, sys type. Isn't that fucking sexy? Do you not agree the sexiness of this? But anyways, here I changed the parameter that set attribute takes. Instead of taking the system type, it now takes the element type. And then in set attribute, where is it? Down here, it uses our map to look up the system type from the element type. Again, I'm just trying to consolidate things, make them central, make one source of truth for our relationships between types. That source of truth is our mapping system here. And then everything just uses the map to resolve that information. And then in asTest, because we changed this one, now it's not templated anymore. So instead of templating on this type, we just pass it in directly as a function parameter rather as a template parameter. All right, and now the final commit of this video. Let's take a look at it because it is extraordinarily sexy. Like I alluded to in the beginning of this video, what we had was we had to define our vertex format at the beginning as a struct, and then down here we had to define it again. We had to repeat ourselves and define it for Direct3D. So that Direct3D at runtime knew the layout of the vertices for various reasons. And now I've replaced that with a single call. So we can take the vertex buffer, get the layout, and then from the layout, we can get the D3D layout. Pass that in directly. And now it's all reactive. We change the layout when we define the vertex buffer, and that'll automatically, this code will automatically change to reflect that. Now we don't have to independently manage two parts of code that have to run in tandem with each other, which again is another source of bugs and just annoying to do as a programmer. Waste of your time. In vertex.h, in order to access this information at compile time about the DXGI format and semantic as a static type, I had to make it static const expression. Otherwise, I would have to actually instantiate the structure before I could access these, and that's no good. Add a function, get desc. This is to the layout. Or no, this is for a single layout element. And we switch the type of the element, and then we call a function generate desc, which takes a template parameter of that element type, and also the offset of that element in the vertex. And then generate desc basically just uses our map to look up the semantic name, the DXGI format type, the offset is passed in, and all the other stuff is fixed, so it's no big deal. And then for D3D layout, we have a function get D3D layout, which just iterates through all the elements and pushes their descriptors back into a vector of descriptors, which is returned. And that allows you to do this, and Bob's your uncle, and it works because I tested it, and it's beautiful. You gotta admit that's beautiful, right? And like I said, this is only the beginning, because in the future, we're going to be using this with our model parsing code in order to check our vertex formats against the formats in the file at runtime, which is awesome. And in the further future, we're going to use this with shader reflection so that our system will load a shader. From the shader, it will get the vertex layout, and then it will generate our vertex buffer layout dynamically from the information in the shader, and that will be used to dynamically generate the D3D vertex layout stuff. and will be used in the model loading. So we'll have one source of truth for the vertex layout, and that will be the shader file. No more of this defining the vertex layout in like 4 different places and having to make sure every time you make a change in one of those places, you have to make that exact same change in all the other 3 places. Oh, I hate that shit, and this system is going to be awesome. And there you have it. Now, some final closing thoughts. First of all, I'm aware, you don't have to let me know this, but I'm aware there's limitations to the system. Some of them we might remediate in the future. Remedy? Yeah, that's probably the word. For example, I mean, you might be wondering, well, with this element type stuff here, well, what if you want, 2 texture coordinates? That's going to be a problem because when you try to resolve texture coordinate, you're only going to get the first one. You're not going to be able to resolve to the second one. So stuff like that will require some changes in the future if we ever need to, if we ever get to. Another valid concern, although I don't respect in general premature optimization. People generally don't understand what things constitute performance bottlenecks and what things don't really matter. But that being said, there's a lot of things that are happening at runtime. For example, when we resolve, we've got to loop over to resolve to the type. That could cause problems in certain situations. Most of the processing of vertices happens on the GPU. It's only usually during loading when we're going to be using these functions. But it might be an issue, and it's something to watch for. It's an interesting thing I want to explore. Stuff like that. So trust me, I'm aware of potential issues, and we'll be, looking into them in the future as they actually become an issue. Cross that bridge when we come to it. Now, second thing I want to say is that this is fairly complicated. All you've got to understand moving forward is the usage of the thing that I've created in this video. And if you understand that you create a vertex buffer by passing it a vertex layout, and if you understand that a vertex layout, you just create that one by, appending elements. That's all you really need to know. There's not really much else to it. It's simpler. It's simpler than the system we had before. It gives us less code in the interface. The stuff that's happening behind the scenes, yeah, it can get pretty nasty, especially if you're not into template metaprogramming. But if you're not into it, you forget it. If you are into it, you just saw a cool little thing, maybe. I don't know. That's my 5 cents. I mean, that's not the traditional quantity of, money that is associated with that idiom, but that's what I'm going with. Anyways, so this is video over. Good times. Next video, we're going to go back to loading models. Now, instead of loading just a single mesh, we are going to start loading a hierarchy of meshes, which is based on a node system. And it's going to be interesting. I'm going to explain some stuff about, the motivation behind why such a structure exists. And then I'm going to show you how to implement the loading. And we're going to render something. It's going to be cool because the model we're going to render is a cool model. But until then, thanks for watching. Hope you enjoyed the video. If you did, please click the like button. Helps a lot. And I will see you soon with some more Hardware 3D.